Welcome to the afternoon session. So it's my pleasure to introduce Professor Robles, and she will continue her lectures about period mappings at infinity and recent developments. Yeah.
Thank you.
Thank you.
So let me begin with a quick review of what we went over last time. So the basic idea is to look at structures that arise in a neighborhood of compact variety and at infinity in a period mapping. And one of the things we get out of those are what you would consider period matrix representations for the period mapping at infinity. And I want to describe how we can use those to study results and construct completions of period maps. Okay, so the basic setup is, again, that I have some smooth quasi-projective variety with a smooth projective completion and a normal crossing divisor at infinity. And last time we broke that down into a disjoint union of quasi-projective subvarieties, which are basically just open strata in the normal crossing divisor. So this is a sort of two-dimensional picture of what's going on. We have over the quasi-projective base a variation of polarized Hodge structure, which includes Hodge bundles. And as has been discussed, of course, these extend to B bar. But that variation of Hodge structure gives us a period map, which is denoted pi with image P. And Schmidt's nilpotent orbit theorem induces from this period map a variation of limiting mixed Hodge structure along each strata. And what this map does is it basically sends a point B at the boundary to an equivalence class of limiting mixed Hodge structures. And this is really just a nilpotent orbit. You should ignore the middle green piece. We have not talked about that yet. That's just a preview. And so we have this limiting mixed Hodge structure, and in particular on the weight graded quotients, the Hodge filtration induces a Hodge structure, and we obtain polarizations from the nilpotent cone of logarithms of monodromy. And so if we pass to that weight graded quotient, we get this, again, a variation of polarized Hodge structure along the strata, and this is the phi naught. And we start by looking at compact analytic varieties that are realized as fibers of these maps. Now, what I said is not quite correct because this map is not necessarily proper. It does not necessarily have proper fibers. But there's a way to take these maps on all the strata and patch them together into what you might call a topological extension of the period map and just call it phi naught. Okay, so it's, I won't go into that again. So even though this is in general topological, and it's not globally analytic, although it's in fact conjectured that it's globally algebraic, as we discussed last time, at this point we only have a topological construction. But it's stratified with an analytic structure. And in particular, in this case, this means that the fibers are compact complex analytic varieties. And we've been focusing on a connected component of one of those fibers, which for convenience of exposition in this talk, I'm assuming is irreducible, but is not necessary. It'll be convenient in a moment though. And then the theorem I finished with last time is that we have a sort of generalization of Schmidt's nilpotent orbit theorem, which you can think of as saying that if you go out to a point at infinity, there's a local coordinate chart around that point where the period map can be represented by a period matrix. What this theorem says is that you can extend that statement to not just a neighborhood of a point, but a neighborhood of that fiber A naught. And I'll forget to say connected component and just call it a fiber, A naught. And so we get a period matrix representation in the neighborhood of that point. And the map, the extended period map, and so in particular the period map itself, remains proper when restricted to where it's defined. Yeah, okay. So there are a couple of corollaries that you can deduce. And in particular, this first corollary has to do not just with the fact that gamma naught is unique, but the result I mentioned last time, which was that this monodromy around the fiber also fixes the reduced period map at infinity. That's the sort of naive limit out in the topological boundary of the period domain inside the compact dual. And you can use that structure to show that the determinant of the extended Hodge bundle is trivial over this neighborhood. And the argument goes essentially the same as Deleuze's original argument that the bundle itself extends out at infinity in the local coordinate chart of Schmidt's that I mentioned a moment ago. But at any rate, what you get from this is that this implies that the augmented Hodge line bundle is also trivial over that neighborhood. And if you remember that conjecture I mentioned last time, which you could think of as an analog of Sataki-Bailey-Borel for period maps, what this corollary implies, if you look at the original argument in Bailey and Borel, and additional arguments in the work with Green, Griffiths, and Laza, then this implies that one can establish that Sataki-Bailey-Borel conjecture for a finite cover if the holomorphic functions on that neighborhood separate these fibers that we're talking about. So the basic problem is to exhibit an analytic structure here or here. And one way to go about it, which was the way that they went about it in Bailey-Borel, is to show that you have enough analytic functions to separate points. And here, by analytic functions, since we're on a topological space that's stratified by analytic varieties, that means you want continuous functions that restrict to be holomorphic on the strata. But then, of course, in this case, since we're actually working on the neighborhood O bar, that just means holomorphic. Okay. So the first thing I want to talk about before we go back to that diagram is how we use this period matrix representation at infinity to construct line bundles and certain canonical sections. These sections will turn out to encode the level 2 extension data at infinity. In particular, they're encoding the nilpotent orbit. And the line bundles themselves are going to be related to pullbacks of sort of theta line bundles that live over extension 1 level data. And I will explain all of that when we get to it. But this is a convenient place to introduce those line bundles. So the first fact to mention here is that since we're assuming that A naught is irreducible, that implies that there is a cone, which I'll call sigma naught, and this is going to consist of this is going to consist of all of the Ni with the property that the fiber intersects the strata Zi. Let me see if I'm saying that the way I mean to say it. I think I want to star here. Okay. I want to work on the open strata. Okay. And we can think of the dual to this cone. So this should be some kind of span over, maybe over Z for this discussion. We can think of the dual of this cone as indexing. And I think I really want generators here. We can think of generators of that cone as indexing period matrix entries. Where the approximating nilpotent orbit lives. very informally. And one of the corollaries that we get out of this period matrix representation theorem we just discussed is that if you pick any element in this dual cone, but particularly a generator, then this gives you a line bundle over this neighborhood. And this is a really naive construction. All we're using here is the fact that over this neighborhood, the period map takes image in a Schubert variety, which is an affine space. It's some Cn with a discrete group action on it. And so to specify this line bundle, I need to give a system of multipliers. And you do this in a sort of naive way by taking exponentials of these period matrix entries and then a ratio of 2. And this ends up giving you a system of multipliers. And with canonical sections attached to them, because you use the period matrix entries to define them. So you get this line bundle and a canonical section. SM, which essentially encodes the nilpotent orbits that can arise as you degenerate to a point on this fiber. And what's interesting with this section is its divisor, which is the just given by the irreducible components of the normal crossing divisor at infinity, weighted with some integers that are coming from the element m in the dual cone. And let me just remark, because it'll be possibly a little interesting later, that if we look at this section in local coordinates inside a local trivialization, so maybe some TW that is in local coordinates at infinity, then the section is basically given by the exponential of one of these period matrix entries, 2 pi I times a period matrix entry. And this works out to be a holomorphic, non-vanishing function, which is not very interesting. And then times a monomial. So you get the TIs raised to the power M and I. And so in particular, it's essentially this local expression that allows one to deduce this formula. Monomial. Okay. And once we get into talking about the extension data, we will see that this line bundle basically encodes the central geometric information that arises when considering the variation of limiting mixed Hodge structure along the strata. There are a number of statements that there are 2 statements at least that's meant to encode. But first, I need to talk to you about the level 1 extension data. And let me go back to the diagram at the beginning to discuss that. Okay. So we had this variation of limiting mixed Hodge structure, and we passed to the weight graded quotient to get a variation of polarized Hodge structure. And that involved modding out extension data. So in particular, fibers of this map parameterize limiting mixed Hodge structures that have the same associated Hodge structure on the graded. So what I want to do is back up one step and be slightly less forgetful. I'm going to recover not all of the extension data, but all of the level 1 extension data, and then mod out everything of higher level. Now the nilpotent cone is level 2, so I still don't see it at this step, which is good and important. So this map is the one that I would like to discuss next. And for that, let me review what level 1 extension data is. So these are the fibers that we're picking up with this phi1. Okay. So, so the fibers of this phi1i, which is defined on the strata, and now goes into gamma I di1. Or rather the fibers of the projection. Okay. Our extension data. So this, let me write it as E1 for short, but its extensions equals 1 to 2n. Of Hodge structures. So here, HK is my shorthand for the weight graded quotient in degree K, along with the Hodge structure that's induced on it by the Hodge filtration and the limiting mixed Hodge structure. Okay. So in particular, this X1K, HK minus 1, these are extension classes of limiting mixed Hodge structures. So in particular, okay, let me slow down and get my indices correct. So HK minus 1, WK mod WK minus 2, and into HK, and then 0. And what's important to us is that this object has the structure of a complex torus. And actually, I'm also going to have to attach some copies of the plane and punctured plane, but we care about the complex torus. Okay, minus 1. So there's the complex linear space, and then we quotient out by F naught of, again, Hom C. And then quotient out by a discrete part. And this discrete part is a surjective image of the monodromy along the fiber. And it's contained in Hom Z, HK minus 1. Okay. So in particular, this extension, this set of extension classes is some complex torus crossed maybe with some copies of the punctured plane. And the plane itself. And since the fiber up here is a direct sum of these X1 groups, that means that the fibers itself is some complex torus, and I'm going to abuse notation and use the same D again. And D prime, because those won't particularly matter. We're not going to be very interested in them. So this guy and this guy, what's important, these are complex tori. Okay. And now the fact, suggestive fact, is that again, this dual to the cone parameterizes what I'll call theta line bundles. LM over the torus. Okay. And the lemma, and this is really just a consequence of the fact that we're working with limiting mixed Hodge structures. So there's positivity inside limiting mixed Hodge structures that come from the polarizations on the weight graded quotients that are induced by the nilpotent cone. And that positivity, along with the the positivity is all I need right now. So that positivity implies the following lemma, which is that this complex torus T inside the fiber contains a maximal abelian variety J that is polarized by those dual theta line bundles with M restricted to sit inside a cone of dual elements that we select using the SL2 orbit theorem. But this sits in, I don't need the I there. Okay. So the point here is just that the dual cone gives us a bunch of line bundles over these tori. In fact, they're defined over the full fiber, but they give us line bundles over the tori, and we can find a non-empty subset of them that polarize the Jacobian variety. And again, that comes from the fact that we're working with limiting mixed Hodge structures. Right, then the theorem here the first theorem a little ahead of myself here. So the first statement is that these quotient maps that retain the level 1 extension data. So the phi I1 would throw out all the extension data except that of level 1. These also patch together to give an extension of the original period map. So phi 1 into, let's call the image p bar 1, and our phi naught factors through this map, trivially. Okay, and the fact that these patch together to give an extension is essentially by the same argument for this map phi naught. Locally, it's the SL2 orbit theorem of Catani, Kaplan, Schmidt, or alternatively the relative weight filtration property. And then globally, you use the fact that the period map is contained in only finitely many Siegel sets out in infinity. Okay, so first of all, these patch together to give an extension of phi. This this map also has good properties. The first is that if I take this level 1 extension data map and I restrict it to my fiber A0, okay, so remember, this is a fiber where the weight graded quotient is constant. So the Hodge structure here is constant. So A is parameterizing limiting mixed Hodge structure, where the only thing that varies is the extension data. And by restricting phi to this fiber, I'm asking how is the level 1 extension data varying along this fiber? Okay. So the infinitesimal period relation implies that this takes value in that abelian variety J. And then third, a computation is that if you take any one of these line bundles that that sits over the level 1 extension data, it could be one of the ample polarizing line bundles, but does not have to be. But if you take any one of them and you pull them back, you get the line bundle that we constructed over the neighborhood of A0, L of M. So in particular, the pullback of the theta line bundle over the level 1 extension data is a sum of normal bundles. Restricted to that fiber. Okay, so this is relating the geometry along the fiber, the geometry coming from the theta line bundle, to the geometry normal to the fiber. And we say not only that this records geometric information at infinity, but it records the central geometric information at infinity, because we're going to see that once you've accounted for the level 1 extension data and the extension data in the nilpotent orbit, which is encoded by those canonical sections, there is no more, the remaining extension data is constant, determined by constants of integration. And this is a non-trivial consequence of the infinitesimal period relation and the fact that we're working on compact fibers. Okay. But the proof of 3 is a calculation with the period matrix representations that are already set up and the construction of the theta line bundles. And 2 is a consequence of the infinitesimal period relation. Okay. So the next fact is the next fact. Let me phrase it semi as a question. So suppose now that we fix a connected component, A1 contained in A0 of a phi 1 fiber. So now we're looking at a compact analytic variety along which extension data of level greater than or equal to 2 varies. So the question then is, aside how does the higher level extension data vary? Along this fiber. Okay, so once we fix the level 1 extension data, what is there left to vary? And by the higher level extension data, here's the level K extension data, for example, sorry, level L, so I could take K greater than equal to L up to 2N. And now I'm looking at extensions that drop down not just one step in the weight graded quotient, but drop down L steps in the weight graded quotient. So these, if you want to think of these as exact sequences, these are the sequences 0, HK minus L, WK mod WK minus L minus 1, and then HK and 0. And the answer is not at all. So in particular, all extension, so I'll say it informally, all extension data not encoded by either the level 1 extension data map or the canonical section SM is constant, locally constant. So in the classical Hermitian case, this is not a particularly deep or interesting statement. It's largely trivial. There is no extension data of level greater than 2. And if you choose a maximal variation, you can realize you can encode all of the level 2 extension data in a nilpotent orbit. So this is kind of an empty statement. But it's very much not an empty statement in the non-classical case. There is higher level extension data in general. But it will depend up to constants of integration on the level 1 extension data and the level 2 extension data that's encoded by these canonical sections. Let's see. Okay. So this constancy has a very, very strong implication. For matrix representations. Okay. As I alluded to a couple of minutes ago, one of the things that we would really like to do is to construct functions on these neighborhoods. We need functions to give an analytic structure, to establish completions of period mappings. And we have sort of partially done that on this neighborhood of the phi naught fiber, the neighborhood of A naught. So we have these period matrix representations, and the entries of the period matrices are functions. The problem is that they're multi-valued functions because of monodromy. And the action of the monodromy, while pretty nice, is not nice enough that one can easily see how to construct these functions that you need to separate points. But this statement here is very strong. And if we restrict now to a neighborhood, not just of a phi naught fiber, but a phi 1 fiber, restrict to a neighborhood of a fiber where the level 1 extension data is constant, then the monodromy becomes very nice. It becomes just about local monodromy. And that means we're going to be able to construct lots of functions. Okay. So let me state the theorem. So the statement is that there exists a neighborhood, O bar 1, contained in O bar naught, contained in B bar, of that fiber along which the level 1 extension data is constant, so that the following 3 properties hold. So first of all, remember that along each of these open strata, we had this map phi1i that was mapping to level 1 extension data. And I mentioned that we could patch these together to get a topological completion of the period map. So this map is itself proper, the patched together map phi1, and it remains proper when restricted to this neighborhood. Okay, now this this map is an extension of the period map itself. So in particular, this implies that phi on O1, which is just phi1, restricted to O1, is also proper. So in particular, O1 is B, intersect O bar 1. Okay, and proper will be important later. The second statement is that the monodromy of the period map over this punctured neighborhood O1 let's call it gamma 1. This is contained in the exponential of the nilpotent cone. And here, I guess I can take a slightly smaller nilpotent cone. So sigma 1 here. This is going to be spanned by the ni's with the property that that A1 intersect Zi star is not empty. So basically the cone of nilpotent operators that I could possibly see along this fiber A1. Okay. So this statement too is what I meant when I said that the monodromy about the fiber is almost as good as the local monodromy. Okay. It's contained in the exponential of a nilpotent cone. And then to make precise this this constancy question that I asked up here, we have the third statement, which we have to be a little bit more careful about. So the variation, it's an extension statement, we have to be a little more careful with. The variation of limiting mixed Hodge structure, not everywhere, but at least on this neighborhood that was given by phi I. So this extends to a proper map to exp. Oh, no, it is I there. Okay. So why did I put extends in quotes? I put extends in quotes because I'm no longer working with the nilpotent cone just along the strata Zi. I have to enlarge I have to enlarge to this nilpotent cone along the whole fiber itself. So I am modding out some information here. It's not quite an extension. There's an additional quotient, but everything that's lost in that quotient is captured in those canonical sections SM of the line bundle. So I still have that data. Okay, but if I throw that out, I get a proper extension of the variation of limiting mixed Hodge structure. And I do not recall if I defined these last time, but these, this is just the union of the Z sub i's that have the same weight filtration. Okay, this stuff can be patched together to get a proper map. And again, this is this Catani-Kaplan-Schmid result, the several variable SL2 orbit theorem, or the relative weight filtration property, and the containment at infinity and only finitely many Siegel sets. Coming from one variable degenerations from Schmid, and in the several variable case from Brunarbe, Klingler, and Zimmerman. It's the same argument again. Okay. At any rate, the kicker is that this map is locally constant. On phi1 fibers. Okay. So e.g. on this A1. Okay. And that's how we make precise the statement that there is no non-trivial extension data, at least that not varies in continuous families in level 3 or higher. And it's also the reason why we say that this is the central geometric information arising at infinity, because it accounts for that can come from Hodge theory, because it accounts for the weight graded quotient, and then built into these theta line bundles over the level 1 extension data. We have all the level 1 extension data. And these bundles know about the canonical sections, which encode the available level 2 extension data. And everything else is constants of integration. So this is sort of all the interesting global geometry that the period map can see at infinity. Okay, so this is kind of amazing. This statement right here. And let me just give you a little example illustrating why this is amazing, and then talk about a consequence of it. So let's go back to this example that we discussed last time, where we had a period domain for polarized Hodge structures of weight equal to 2 and Hodge numbers 2b2. And we talked about a period matrix representation. Which I will just write as phi, but maybe here to be very, very careful, we should restrict this to this punctured neighborhood of the phi1 fiber, where I want to make some statements. So as I wrote last time, we get something like this, and then we have 2 columns, and it doesn't really matter how these are indexed, but two. Let's write the period matrix like that. So the first summoned, or the first Hodge filtration, is rank 2, because the first Betty number is 2. And these 2 rows are just specifying a basis for that summoned. Okay. This domain is not Hermitian, so the infinitesimal period relation is non-trivial. And that means that I can talk about the horizontal part of the period matrix. So this is the horizontal part. Okay, and that's something that you can check directly and easily from the basis I initially set this example up in last time. Okay. So this stuff is not horizontal, but the IPR says it's determined up to constants of integration by the horizontal part. So I'm going to think of it as being constant because once I know what's going on here, this is discrete data. Okay, now, so right now it looks like I have a bunch of functions on this neighborhood. Each coordinate is a function. But the functions are only defined up to the action of the monodromy. But this monodromy that we're dealing with is very simple. Now, it's kind of a mess on the non-horizontal part, but again, I don't have to carry about that because of the infinitesimal period relation, so I'm going to ignore it. And then the only matrix entry in the horizontal part that the monodromy acts on is this component. Okay. So the statement is that 2 implies that the horizontal CAI that are not equal to this singleton entry are well-defined, single-valued holomorphic functions, O bar 1 into C. And the one that's left, because of the monodromy, exp 2 pi I from O bar 1 into C is also holomorphic and well-defined. Okay. So the upshot is that we have a proper map. Let's call it F from O bar 1 into some Cn. And it's a proper map that is locally constant on 5 fibers and vice versa. And again, because of the infinitesimal period relation. Okay. So for this statement here, locally constant and vice versa, all I need to do is have control over the horizontal part of the period matrix, and F is exactly control over the horizontal part of the period matrix. So as a result of this, you can now apply Catani, Deligne, Kaplan, and a result of Grauert to prove the following theorem. So there exists, well, wrong page, already proved that. Blah, 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 functions. Okay, let's assume that gamma is neat. Then the first, I'm a little carried away with myself. Carried away. So before I state the theorem, let's look at the Stein factorization. I need to work with a period map that has connected fibers because of this whole up to constants of integration business that I've been discussing. So we are going to take the Stein factorization of the period map, which I can assume without loss of generality is proper. So I'm assuming that my original period map is proper. This is the image. And then the point here is that the fibers are finite. And here that the fibers are connected, which I need since I'm working up to constants of integration. Okay. So now we're talking about a finite cover of the image of the period map, and we're going to assume that gamma is neat. Then the first statement is that this p hat, this finite cover of the image of the period map, this is Zariski open in a compact Montgeon space. P hat T. And this finite cover, phi hat, of the period map itself extends. And it extends as in we have B is included in B bar, and we get a phi hat. A diagram like this extends and is a morphism. So let me sketch the proof for you, the idea of the proof, which is quite simple now. But let me, before I do that, also mention why there's a superscript of T here. So what does this space that we construct parameterize? So this space is going to be constructed so that it parameterizes fibers of this map F. So that means that it's going to parameterize up to constants of integration, the period map, and the limiting mixed Hodge structures at infinity. So we know by the work of Carlson, Catani, and Toledo that likewise the toroidal constructions admit a similar interpretation as parameterizing. You get the boundary components by attaching equivalence classes of limiting mixed Hodge structures at infinity. So it seems to us that this is an analog for completions of period mappings of that construction, and that it encodes all of the Hodge theoretically available information at infinity. It encodes the limiting mixed Hodge structures, modulo some equivalence relation. Simply virtue of the way it's constructed from these functions. So the idea of the proof, or the outline of the proof, is the following. So we're going to look at the set of all pairs, B1 and B2, inside B cross B, so that they have the same image under this period map that we're trying to complete, this Stein factorization period map with the connected fibers. So this defines an equivalence relation. On B, so that the image of this period map, P hat, is of course just the quotient of B by this equivalence relation. and the period map is the quotient. Now, the result of Catani, Deline, and Kaplan from 95 tells us that there exists an algebraic variety, X bar contained in B bar cross B bar, so that this equivalence relation is algebraic in the sense that it's cut out by this X bar over B cross B. Okay, so now suppose that this X bar defines an equivalence relation that is two things, a proper holomorphic equivalence relation on B bar. Then a result of Grauert's, those two, a result of Grauert from 83 tells us more or less that we're done. It tells us that P hat T, which is the quotient by that equivalence relation, is complex analytic. And that phi hat, we can take phi hat from B bar to P hat T to be the quotient map. Okay. All right, so we're almost entirely done. I have to address this business of a proper holomorphic equivalence relation. I should also thank Greg Perlstein, who first mentioned to me several years ago that thinking about equivalence relations was one way to approach this problem. The only thing that's missing here is that I said that the object that we constructed would be moigejean, not just complex analytic. But this is something that you can deduce from general results on moigejean varieties. It's in this book of Anacana and Tomasini. And then you need the fact that Artin has some results that extends some of Serre's Gaga to these moigejean spaces. It's fairly straightforward. And I have to thank Daniel Greb, who pointed that out to me. So all I really have to do is find this proper holomorphic equivalence relation. So what I need to do for that is to construct locally a proper holomorphic map that coincides with the fibers, whose fibers coincide with those of whose, that's very bad, it's an inconsistent notation, whose fibers coincide with this map. But to do that, I just take the Stein factorization of this map. And then the infinitesimal period relation tells me that the fibers of this map, when restricted to the intersection with B, are the same as the fibers of this map. And that gives the proper holomorphic equivalence relation that we need. So the idea of the proof is to take the equivalence relation perspective, use the functions that come from these period matrix representations at infinity, and then apply Grauert. And I'm out of time, so I will stop here.
Thank you. So is there any question or comment? I may ask you one very stupid question. Indeed. Yeah. So how can I say this description of this extension of this period map. So is there some very concrete example one can really compute what you describe very explicitly?
So I think certainly you could work out relatively easily, I mean, some classical examples with D Hermitian because that's very well understood and explicit. But then what you get should be something very much like the toroidal construction of Ash-Mumford and Rappaport-Tai, if it's set up correctly. We have not thought, it's a very interesting question of whether or not you get exactly the same thing. We haven't thought about that carefully. It seems they must be very close because what you're attaching at infinity is parametrizing essentially the same object. And then if you wanted a non-classical example, so when the period domain wasn't Hermitian, and you wanted it to come from, I mean, you could cook something up relatively easily if you were just fooling around with the infinitesimal period relation and looking at, say, maximal integrals of the IPR on the compact dual. You could do something formal. But if you wanted an example that actually came from geometry, like a family of eye surfaces or something like that, you would actually need a way to, given that variation, write down the period map explicitly. And I think the period map is often difficult to get your hands on in that kind of concrete detail. So I don't have a sense of whether or not that's possible. I would guess maybe not.
Colleen, I think for the case of the eye surface, the boundary, I mean, there's a difference with the classical case in that if you take the period mapping, say, for curves, for smooth curves, that extends to mg bar mapping into Voronoi 2 toroidal compactification. Here in the non-classical case, like for the eye surface, the period map will extend to Satake-Bailey-Borel, but not to these toroidal compactifications. What the toroidal compactifications are doing in the examples so far is desingularizing the boundary components of moduli, among other things. So even though that's not a formally written out result, at least at a general point of the boundary components of the eye surface from the examples in the literature, that's what the effect of this map does, which is quite different from the classical case, where the compactified moduli space is basically smooth.
I see. Yeah. Thank you.
So may I have a question? May I have a question?
Yes, yeah, go ahead, King.
Yes, in your last theory, why you need to assume the first Hodge boundary has to be rank 2?
Oh, I don't. No, that was just an example to give you a feel for where the functions come from. That last theorem is for arbitrary period maps.
Okay, so maybe.
But I'm just not willing to write down a period matrix that has more than 2 rows in it. You only give me an hour.
Okay, thank you.
Okay, other questions or comment? Okay, if not, let's thanks the speaker again for her wonderful lectures. So we will resume tomorrow 9 a.m. in Miami local time.